Notes for today, this is the last part of the notes for chapter 8, because chapter 8 is only about confidence intervals. That's all it is. One sample confidence intervals. So we've done some proportions. We did several days on proportions. So the last part of it is means, all right, averages. With means is a little different though. With means is a little different because we have two different types of intervals. They both are means and they're both very similar. They have the same steps, but they're different. One is T and one is Z. We've used Z quite a bit. Z is the Z score, it refers to the Z score, right? When do we use that one? We use that one when this guy is given, when the population standard deviation is given in the question, the problem, the prompt. If it's given, we use Z. If it's not given, like almost every single problem you see will be not given. Okay? Then we use T, which we've never used before. We're going to learn about T today. What's the difference and why do we use one? Well, why we use one? Because of the population standard deviation. Well, in real life, you're never going to have Z. Because if this is given, if this guy is given to you, if we know this, what do we also have to know? Not the population. The true what? There you go, right? We also know this, right? And if we know this, then why the heck are we doing a confidence interval to get an interval, right? It's like showing you the pennies and saying, okay, there are 1,632 pennies in here. How many pennies do you guys think there are in here? Exactly, right? It's a waste of time. Why would you do that? Why would I ask that question, right? So this one is not practical, and I've never seen it on a test, but it is. What's that? There's always a chance. There's always a chance. And I would say 99% of them are T related, right?
Are we going to find the confidence interval for that?
Why do we use Z? Because there's always a chance. And it's covered. It's one of the standards that we've covered that is covered. You have to know one sample Z. Okay? So I just say that going ahead. Going ahead, if you're going to pick one that I know really, really well, it's going to be T. Okay? But Z is also something you should know because it's one of our standards that we need to cover in this class. Okay? And it could be tested. Okay? But on AP test, I've never seen a Z, one sample Z. I've seen plenty of one sample T's, but never a one sample Z. Okay? That doesn't mean in our tests for this chapter, I'm not going to throw in a Z. I might do that because it's just one chapter, right? But if you're looking at a whole AP test, they usually focus more on T. Okay? Okay, so that's the reason why. Because if we have Z, then we know this and we also know this. So why am I predicting something that I already know? Okay? If I don't know this, then I don't know this either. That's why I'm predicting, because I don't know. Okay? Okay, so what is T? Since T is the one we're going to focus our time on, what is T? Why is it called T? Well, T procedures. When the standard deviation of the population is unknown, real life. What does this mean for means? The student's T model. It's called the student's T model. And you notice student is capitalized. It's not because it's talking about you guys, students. It's the guy's actual name who discovered this and developed this. His actual last name was student. Okay? So that's why it's students. It's named after him. Okay? So yeah. So exactly, like normal, right? Normal curve. You think normal, it's not normal, that's the guy's name, normal, who discovered it. So it's capital, that's why it's capital N and capital S. Okay, so the reason we use these is when we don't know. So Z is based off of knowing this. Z is the perfect world where we know this, right? But that's not real life. Real life isn't perfect, right? So we've been basing everything we've done from chapter 1, chapter 2, chapter 3, chapter 4, all the way to now. We've been basing it off of this nice, pretty world that exists that really doesn't exist, right? Because Z is based off of knowing this, which means I know this. But in real life, we know that that's not possible, right? Unless the population is really small. If the population was our class and we were trying to find the average height, then I could know that, right? I would just have you guys measure yourselves, add them up, divide by 6, because there's 6 of you right now, and I could get that, right? So if the population's small, it's possible. But if the population is the city of Fresno, residents in Fresno, residents of the state of California, even if it's students of Central High School, it's going to be really difficult to get that. Okay? So we use T instead. Okay, so if I don't know the true population mean, if I don't know what the true population mean is, we have this situation here. So look at let's start with the picture. The picture here. You see the dashed line. The dashed line is the normal curve, the one we've been working with since chapter 2. The solid line is a T with 2 degrees of freedom. I'll explain what degrees of freedom mean in a second. But what do you notice about the dashed line versus the solid line? Let me change colors so it's a little easier to distinguish. There you go. The yellow is the normal. The green is T. That's what it is. Which one has less variability? The green or the yellow has less variability? Yellow. Yellow has 0 variability. 0 variability because it's based off this magical world that doesn't exist. The perfect everything. All right. Green is the world we live in. There's going to be some variability. All right. That's what T is. Degrees of freedom, which we'll explain on the next slide. Degrees of freedom. As degrees of freedom goes up, we get closer and closer to that real world that doesn't exist. So if we had infinite number of degrees of freedom, we would be in Z. That would be Z, but it doesn't exist. So as we get more degrees of freedom, okay? The curves have more area in the tails because we are using S. S is the standard deviation of the sample. This guy here is the standard deviation of the population. We don't have that, so we have to estimate that. So with that comes uncertainty and variability, just like we said. Okay, so degrees of freedom. What in the world do degrees of freedom mean? Degrees of freedom, how we calculate degrees of freedom is n minus 1. N minus 1. What is n? What does n represent in words? Sample size, right? So as sample size goes up, so does degrees of freedom, right? So df equals 1 means I have a sample size of 2. df equals 2 means I have a sample size of 2. Or 3, sorry, 3. df equals 5 means I have a sample size of 6. df of infinity means I have an infinite sample size, which I can't get, right? So df, so normal would be df equals infinity. Degrees of freedom equals infinity. That's never going to happen, right? So more than likely, I'm going to get a degree of freedom of some value, right? Some value. So this part is important. As degrees of freedom goes up, variability goes down. Okay? So something with a little degree, with a small number for degrees of freedom, huge variability. Huge variability. But as degrees of freedom gets closer and closer to infinity, we minimize variability. Okay? That's the main thing. Okay? Degrees of freedom. You're going to be hearing that for the rest of the year. Degrees of freedom. That's what degrees of freedom are. It's based off the sample size. As sample size goes up, so does degrees of freedom. And when they both go up, the variability goes down. Okay? So here's some red meat for multiple choice questions. These are multiple choice questions waiting to happen. When we don't know the population standard deviation, we use the sample standard deviation, which is S. We call it S, lowercase s. Okay. So you'll see on your calculator, maybe you've seen it before, where you see this guy here when you go 1 var stats, you've seen this guy, and then you've also seen this guy. They both mean the same thing. One comes from the population, one comes from the sample. Okay. But the population, so if I put numbers in L1 and that's the population, then I'm going to use this guy, right? But if it's not, what it does is your calculator it estimates what the population would be. Okay. So for the most part, we're going to use this guy when we're calculating our standard deviation. Okay. T-distribution has fatter tails. What does that mean? We talked about it. I didn't use the word fatter tail, the phrase fatter tails, but what does fatter tails mean when I'm talking about this picture here? There you go. Yep, that's what I mean by fatter tails. More variability, more spread, or more variability. More variability. Okay. As degrees of freedom increase, the T models look more and more like the normal model. Right? That's the perfect world. Normal model's the perfect world. We'll never get there, but as we get more and more degrees of freedom, we get closer and closer to that. Okay. In fact, the T model with an infinite degrees of freedom is the same thing as normal, is exactly normal. So when we say roughly normal or approximately normal, that's one of the reasons why, because of that, right? To be exactly normal, you would have to have an infinite number of degrees of freedom. So that means an infinite population or sample size. We don't get that, right? So we always say approximately normal or roughly normal. Okay. Okay. I'm going to skip the equations for now. So skip the next two and go to this page right here. Skip the next two. We'll come back to them. They're just formulas. They're both very identical. And we'll spend time on them. Don't worry. But I want to go here. I want to practice with T's because we haven't done T at all this year. So on your tables, on your z-score tables, on the back of your z-score tables, you should have something that looks like this, where the left side has this guy that kind of looks normal, and the right side is something that's skewed, right? The guy on the left is T. The guy on the right it's like a cursive x squared. It's the Greek letter chi, so it's chi squared. We'll do chi squared in about a month. So don't worry, we'll come back to chi squared, but for today we're just focusing on T. So how you read it is similar to the z-score. It's not the same, but it's similar. So for example, let's say we have a sample size of 20 and we're doing a 95% confidence interval. How would I get my T critical, right? Z critical, we use the table, right? Z critical, we use the tables we did at the very beginning of the chapter. These guys here, right? Z critical, we use those. How do I get T critical? Well, this is how you do it. First thing you do is you start with the degrees of freedom. You got to find the degrees of freedom. So degrees of freedom, what is degrees of freedom going to be for a sample size of 20?
19.
Good. So go along the sides here and find 19. Right there, right? Okay. Next thing you're going to do is what percent is my confidence interval? 95. So if you look at the bottom, you have confidence levels there, right? Match them up. Where does 19 match up with 95?
2.093.
2.093. Yep. Guess what? That is my.
Is this given on a test?
Yes.
This?
Both sides. Yep.
Even on the AP test?
Yes. I haven't given it to you because you haven't needed it on any tests. I've only made the copy of the front, but it is. Both of those are given to you.
It has the Z scores on the bottom.
Exactly. Right? It does have the Z scores. If you look on the bottom are all Z scores, right? Because that's based off a infinite degrees of freedom. So with a 95% confidence interval, what is the Z critical value?
1.9.
There it is right there, right? Now what is ours? Ours is bigger, right? Because there's more variability. There's more variability, so it's bigger. The fatter tails are causing it to go out a little bit. Okay? But as I get a sample size that goes higher, it gets closer and closer to that 1.96. If I had a sample size of 1,000, it'd be pretty much 1.96. Or sorry, sample size of 1,001. Okay. Okay, so do the rest. Do 2, 3, and 4. Yeah, after so number 4, after 29, it goes by tens, right? So degrees of freedom here for number 4 is 49. That's not on my list. Yeah, you use exactly what you said. You use the one that's closest to it. The one that's closest to it is 50. Is that exact? No. But it's the best we could do with the table. So with 50 and 98%, we get 2.403. If you want a closer estimation, your calculator will do it. I'll show you how to do it on the calculator. Your calculator also can find T as well. Okay. All right, so answer the next page. So the bottom has questions also pertaining to T. So I'll give you a few minutes, answer those. So there's 6 questions. Yep, 6 questions. Okay, so the first 2 are based off a 95% confidence interval. One is 20 based off, they're both based off sample sizes of 20. So why we've been using 1.96, but the one that's based off 20, the T score or the T critical value that's based off that is 2.093, which I think we got in the first one. Yep, it's the same as the first question on the last page. Why is there a difference? What did we say? Why is there a difference? Which one's further away from 0? T or Z? T. Why is T further away from 0? More variability. Because, oops, sorry, put because there is more variability with T.
Lord, how do you get those numbers?
Let's see.
Did you subtract 1 from the sample size?
Yeah,
You did?
degrees of freedom. So 14. So let's see, 14.
No, the first one's right. The second, the last 4.
The last two?
Yeah.
Okay, let's see. 10, so it'd be 9 degrees of freedom, 98%.
2.821 is what I have.
Oh, yeah. Yep. 2.8. This one right here?
I have 2.365.
2,
Yeah, I have
8.
365 on the last one.
All right, let's see. 95 with 8 degrees of freedom, 95.
No, 7 degrees.
7 degrees of freedom, that's probably what I did. 2, 3, 6, 5? Okay. Okay. So we've been doing things with z-scores, right? This is only for means. Here's the thing. Z, there is no such thing as T for this guy right here. For proportions, there's no such thing as T, only Z. So that's where it's easy. Proportions, don't even have to worry about T. The only place where T exists is when you're dealing with means, okay? So don't worry about T for proportions, only with means. That's why we did talk about it the first time, right? Because there is no means in proportions. It's just the true proportion, right? You're not finding any averages, okay? Okay, um, so with confidence intervals, it's the same 5 steps. Now, they're not going to look exactly the same. Number 1's going to look different. Number 2's going to look different. Number 3's going to look a little different. The third condition is going to look different. Calculations are still calculations. Conclusion is the same. Conclusion is the same. You scroll down a little further. It's the same conclusion. The only difference is instead of true proportion, it says true mean. Okay. You're still doing that. All right. Okay, so the first one has changed because with proportions, we had P equals true proportion of whatever. Yeah, go for it. With this guy, it's going to be the true mean, right? So we start with true mean, blah, 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 whatever it is. Okay. Test statistics going to be different. They look similar than the last ones we did, but they're a little different. So this is for Z. This is for T. Looks similar to, right? Instead of P hat, we have X bar, which is the mean sample mean. Sometimes we have Z critical if it's Z. If it's T, we have T critical. And then over here, we have the standard deviation. If we have this guy, we plug it in over the square root of n. If we don't have it, that must mean it's T, and we find the standard deviation of the sample and do it that way. Again, this part right here is the measure of the margin of error. That part's the margin of error. This guy right here is the point estimate based off our sample, right? You guys know how to find T critical. We just worked on that. That's how to find T critical. Z critical is still the same, right? We look at our table. The Z critical only depends on the confidence level, right? So if we decide it's Z, all that matters is the confidence level, okay? Let's see. Conditions, 1 and 2. Number 1 and 2 are going to stay the same. So conditions number 1 and number 2 are exactly the same. Nothing's changed from proportions. Okay. The only thing that's changed is number 3. Number 3, we don't do n times p is greater than or equal to 10 n times 1. We don't do that because we don't have p's. So what do? Here's all 3. Number 1 and 2, like I said, it's the same. Number 3 is different. So we have 3 options for normality for number 3. First option, they tell us in the question that the population is roughly normal or normal. That's the easy one. Number 2, they don't tell us, but our sample size is big enough, bigger than 30, so we can use the central limit theorem, which we did last chapter as well. Third one is a new one. None of A and B, or sorry, 1 and 2 are not true, or we don't know 1 and 2, so we have to use this guy here. So this guy is create a graph, either by hand or using the calculator real quick, and check for outliers or strong skewness. We can have skewness, but strong skewness. So things that are very skew. So something is very skewed to the right if almost all of the data is on the low side. And we have a few points on the right. It's skew. So in terms of, so if it's skew right, it would be like a test where almost everyone scored terribly except for 1 or 2 students. If it's skew left, it would mean the opposite. Almost everyone got a 100% on the test except for a few students who like failed, right? That's what strong skewness means. Okay. And of course, outliers. What would we'd probably call of those students who either scored on the high end or the low end, we'd probably call them outliers because they're so far away from everyone else. So they usually go together. And our calculator has a way of easily calculating outliers using the graph. We have a graph where it'll calculate for us. Okay. We only use that though when we need to, when it doesn't pass number 1, doesn't pass number 2. All right.
Do we have to show the graph?
Just draw a quick sketch of the graph. That's what we use the calculator for. It says use a dot plot, but if the dot plot's big, like if there's a lot of data on it, then it's going to be less than 30, but still, if there's 25, I don't want to draw 25 points of data. So what I'll usually do is draw a box. So what I'll usually do is use the calculator to draw a box plot, because the calculator draws box plots really easily. And if you choose a modified box plot on the calculator, it'll actually tell you the outliers. Yeah, it'll mark the outliers by a star or something. Okay. See anything else? Calculations based off our conclusions, the same. Okay. So let's do one. Let's do one problem today. Okay, first question. Mr. Flores is curious about the mean GPA of students at Central High School, East and West Campus combined. Okay, so East and West Campus combined, you're talking about over 4,000 students, probably closer to 4,500 students. So he decides to take an SRS of 40 students to help him answer that question. The sample mean for the 40 students is 2.98 GPA with a standard deviation of 0.54. Use this to construct a 98% confidence interval for the true GPA of students at Central High School back when we were one high school. Okay, so East and West combined. Okay, so first thing we always do, pick out the pieces that are important. What's the important stuff that we're going to need? Sample size of 40. Good. So n equals 40. That's important. We're going to need that with our calculations and with our conditions. What else?
Sample mean of 2.98.
So 2.98. What symbol goes 2.98?
X bar.
X bar. Good. Keep going. 98 confidence interval. That's definitely important.
And then standard deviation of 0.5.
So what symbol is that? The O with the tail or the S?
Sample standard deviation.
Good. Good. That's definitely important as well. Anything else important? There's 2 more things that are important. One thing's on there, one thing's not. There you go. This is going to be our first step right here, right? That's our first question. That's going to be the first true Mean GPA of students at Central High School. That's what I'm trying to figure out, right? Population parameter. First step of our first step, right, is identify population parameter.
Yeah.
So it'd be mu equals that.
Yeah.
Yep. One thing that's not written there that's going to be extremely important. You guys already said means. Means is important. It's kind of obvious because it's on the means notes, but that's also important. On test day, it will not be given to you, so you have to decide that. So that's a good point. There's one more thing that's important that is not on here, is not written in here, but it is important. Think about it for a second. What do you think? What else am I going to need? No, even before that. Even before that.
The degrees of freedom?
Even before that. You guys are dancing around it.
Oh, it's Z.
Is it Z or T? That's what I'm asking. Is it Z or T, right? Because if it's T, we're going to need T critical values. We're going to need degrees of freedom. If it's not, if it's Z, then we don't even need to worry about that stuff. So let's go back to the problem and decide which one is it and how do we know? So the reason why we would use it is if we use T is if we don't know that guy. Do I know that guy? It's not given to me and I don't know it, right? So this is a big question mark. So because of that, we're going to use T procedures or a T model. Okay. So that means we're going to use that second equation here. Okay. Okay. So let's start with population parameter. Okay, population parameter. So mu equals true mean what? Yep, that's why we picked it out. True mean GPA of students at Central High School. Done. 1 point. Second one. Um, so test statistic or formula. Test statistic. You don't have to go in order, but as long as they're all there. So this one's not population parameter. I keep forgetting to label them. It's important to label them so they know what they're looking at. Okay. So we're going to use X bar plus or minus T critical times, and this part, the last part is on your formula sheets. Okay. Conditions, assumptions.
Oh, SRS first. SRS.
SRS. How was the 40? Was it taken in a proper procedure?
Oh, you did it. So yeah.
Yeah, it says SRS. So SRS means it was done in a simple random fashion. So hopefully I know how to do that. Stated. I have no reason. We have no reason to question it. So we just go on with it. Okay, so next one, 10%. So n is less than or equal to 10% of big N. So n is 40, less than 10% of, if we could either write it or we know it's going to be at least over 4,000. So we would say 4,000 plus. So at the lowest, it's going to be 4,000. I think 1% of 4,000 is 40. You could put that too. All students at Central High School, you could write that as well too. Yep. Either way, it gets a check. Number 3, normality. Okay, so this is where we're not going to use p times n times p. Okay. So we have 3 options here. So let's go back over the 3 options. 3 options here. Option 1, in the question it was given the population is roughly normally distributed. I don't recall them saying that anywhere in there. If they did, I would have highlighted it, and I didn't, so nope. They didn't, but the sample size is large enough, so by central limit theorem, we can assume normality. Yep, that's the one we're going to go with. Number 2.
You only have to make one of those, right?
Yep, only have to do one. Start with number 1, go down the list. Always start at the top. Since n equals 40, we can assume normality using central limit theorem. Okay, good. Okay, next one is calculations. So let's use that formula that we stated earlier. Calculations. Okay, so x bar, what was x bar in our case? Plus or minus. T critical. So how many degrees of freedom are we going to have on this question here? 39, yeah. 39?
Basically 40.
Okay, so we have to use 40.
98.
It's a 98% confidence interval.
4.423.
Say it again.
2.423.
There you go. 2.8423?
No, 2.423.
2.423.
Yeah.
Okay. Times. So we're going to have the square root of n down here. So that's 40. Standard deviation. What was the standard deviation for the sample? Okay, so about half a grade. That varies by about half a grade. Okay. So from here, you can crunch the numbers using a regular calculator, or you could go to stat tests. Okay. So let's do that. Let me get my calculator running and we will go. Because again, there's quite a few interval ones, interval options. Now we're not going to choose anything that says proportions. So anything that says proportions, automatically not going to choose. We're not going to choose anything that says 2 because we're not doing 2 sample. We're only doing 1 sample. So it limits them. And we're not going to do anything that says test, only interval. Okay, so let's scroll down. So 7 and 8 are Z and T interval. Could be those, right? Okay, let's keep scrolling down. Stops at B. A, we use 1 proportion Z interval. We used that one last time. That one's not going to work there. 2 sample Z, 2 sample T, those don't work. So the only options, yeah, are 7 and 8. 7 and 8 are the only options. And this one is A, T, so we're going to go to T. Okay, so it gives us two options now. It says data or stats. Data means I actually have the numbers. So you actually have the GPAs of all 40 students. I don't have that. So I'm going to go to stats. I know the statistics of those 40, but I don't have each of the 40. Sometimes you will. Sometimes you will, and you just put data, and it just tell it where the data's at. So here we go. X bar was 2.98. Standard deviation was 0.54. Sample size was 40. Confidence level, 0.98. Calculate. Okay. So our interval goes from 2.7729, so a high C, C plus average, to 3.1871, which is a B, low B. Okay. Based off our point estimate was 2.98. Our standard deviation for our sample was 0.54, and our sample size was 40. Okay, so let's go back to this guy. Okay, so the last thing is conclusion. So conclusion is the same conclusion, just one word differently. So the conclusion, where is it? Right here. We are blank percent confident that the true mean blank is between blank and blank. We are 98% confident that the true mean, we go to our population parameter, which is the first thing we did. We literally cut and paste. True mean GPA of CHS students is between 2.7729 and 3.1871. Done. Okay, so we did the confidence interval. 98% confident that the average of all, if I took the average of all 4,000 plus students based off my sample size, and I found that average, that it would be somewhere between 2.77 and 3.19. Okay. Okay, so now there was a sub question to that. There was a sub question on there. A brochure given to prospective eighth graders says that the average GPA is 3.15. Do we have sufficient evidence to change the brochure and say, nope, it's wrong? We do not. Why not? We do not. So let's put that. We do not.
Because 3.15 is in the.
Exactly. Unlikely, but still possible. We do not have.
So I'm guessing the likely one would be the mean in the middle, right?
Yeah,
The likeliest one.
closer in the middle.
Closer to the mean.
We can say, though not likely. You don't have to put that, but you can if you want, if it bugs you. We do not have sufficient evidence because 3.15 is within our interval. Okay. Alrighty. Okay, so tomorrow we're gonna continue on. We have one more question on here. dealing with cookie question. And then, yep. And then at some point, we're going to go back to our list of students and find their average GPA using a sample size of 25. Or you might want to make it 30 so it passes number 3. So we might want to do that when we do it again.
If the question isn't normal, do we still do it?
Yes, you just state cannot assume normality because, and then you keep going. You don't stop. Mm-hmm. Yep.
On the homework, when it says like if the question states that's an estimated probability, is it PR? Like it says that certain company estimates probability. Yeah, those are the last 2 questions.
So if it says estimate isn't necessarily, it just depends if it comes from the population or if it comes from the sample. So which question was that? Do you remember?
41 and 42.
41?
Yeah, it's like.
41 video games. Here we go. So it estimates that 49% of US adults. So that 49% goes with US adults. So that's going to be P.
Yeah, so
there you go.
Yeah,
He didn't listen?
No. Okay, do we have enough time? We have 3 minutes.
Yeah, give me a second. Let me, which question? The same question?